So what I want to do in this lecture is look at these equations that we derived in lecture 3 and apply them. So to remind you, this left column is how you can solve the position x, the velocity v, or the acceleration a of a particle moving with simple harmonic motion as a function of time t. So if I say here's the time, you just plug it in and then you get either position, velocity, or acceleration. The only exception to that is this bottom bullet point, which is the formula we derived that allows you to solve with the acceleration as a function instead of position x. The right column is what you will use if you're asked for the maximum value of any of those three quantities. You might want to either take a picture of this slide or write these equations down, as we're going to refer to them repeatedly throughout this lecture. Go ahead and read the prompt here, and then we'll talk about it. Before I let you try to solve some problems with this, I want to just show how the equation in the prompt relates to the generic equation we've been talking about. So in this case, I've tried to color code it to make it make more sense. We can pull out three quantities. One is that the amplitude is 1/2 or 0.5. The other, well, one of the other two rather, is that omega is pi over 3. And then the third one is that phi, or the phase angle, is negative pi over 4. Once again, the negative sign here denotes that we have a rightwards shift, whereas a positive phi value would have denoted a leftwards shift. Okay, that's all you need. Please pause the video, solve these two parts, and resume when you're ready. Before you solve this problem, just note that the three quantities we derived in the last slide are here at the top. Go ahead and pause and solve part C. Why would there even be a maximum force? That's what I want to talk about before we solve the problem. So maximum force, well, that implies that there's a different force. Force changes in some way, and that's consistent with what we know about springs. Springs obey Hooke's law, which tells us that the force exerted by a spring is directly proportional to how much you have displaced that spring. In other words, if I stretch a spring, it pulls back towards where it started. But if I compress a spring, it pushes back towards where it started, always against my motion. Springs are contrarians in that way. And so to solve this, we'll just use Newton's second law that the force equals ma, and the reason I've omitted the sigma, the sum of forces, which is really Newton's second law, is because the only force present on a frictionless horizontal surface in the x dimension, which is what I'm analyzing here, is the spring force. So F is just the spring force, or it's also the net force. Well, what net force do I want to use? Well, maximum, the maximum force. When do we achieve maximum force? That occurs when the acceleration is also maximized. So yeah, these are directly proportional, so they move in tandem. So therefore, if I want F max, I have to use A max. And that's useful because we have an expression for A max from earlier in the presentation and from lecture 3. So that's omega squared times amplitude. If I substitute the value that we already know for mass, 4 kilograms, omega is pi over 3, and amplitude is 0.5. We can solve this, and I just want to make one mathematical note, because I see people make this mistake frequently enough that it bears mentioning. When you square a fraction, you do have to square both the numerator and the denominator, so this becomes pi squared over 3 squared, or pi squared over 9. Then that gets multiplied by 4 and 0.5, yielding 2/9 pi squared, or in decimal form, about 2.2 newtons. That means, literally, this subscript is so important here. The force the spring exerts at its greatest magnitude is 2.2 newtons. Other than the amplitude, which is, again, when the force is maximized, this is something smaller. The force is only 2.2 newtons when position from equilibrium or displacement or, again, amplitude, when that has been achieved. At every other time, force is something else. Here in part D, I want you to try to find the spring constant K. Please pause. So this one might be a little bit tricky in terms of like how do I start, because we don't have an equation from the slide earlier that had all the equations on it that has K in it, but you do know that there's a K in a few equations. I mean, really only a couple equations, one of which is the energy equation, 1/2 kx squared. That's for elastic potential energy, but this is not an energy problem, and this doesn't even talk about energy. So instead we'll use the other one, Hooke's law, which tells us that the force exerted by a spring, or the restoring force, sometimes called the spring force, is equal to negative this spring constant K times x, which is the displacement from equilibrium. The reason that I've chosen to use the subscripts max and max is because, one, whenever we want to find the force exerted by a spring, we must find that force at a particular displacement. So these have to correspond to each other. And two, we already know F max because we found it in the last part. So I want to use F max because it'll allow me to solve for X max, although you can actually solve for the spring constant at any corresponding position in force value, but we don't know any other corresponding position in force values except 0, 0, and all we would be able to do with that is 0 equals K times 0, which is kind of useless. So subbing in the value of the F max, which is 2.2 newtons, and you'll notice that I've changed the amplitude, which was positive 0.5 up here, to negative 0.5. The reason is because they're vectors, and so if the force is positive, and in other words, I haven't included a negative sign, this is implied to be a positive value, or to the right. If the force is pushing me to the right, which direction must the spring have been compressed? It must have been compressed leftwards, and therefore this is a negative number. These negatives cancel out, and your K, or spring constant, is 4.4 newtons per meter. Pause again, try to solve for example 2, part A. You may have been tempted to go the same route, use the same strategy that we did in the last video, which was, oh, I want the amplitude. Well, that's the same as the highest point or the lowest point, in this case 3. The reason that's wrong, unfortunately, is because this is not a position versus time graph. So these peaks and valleys do not represent the maximum displacement from equilibrium. They represent the maximum velocity. Velocity max is 3 or negative 3, or you could sort of equivalently say speed is maximized at the value 3 meters per second. So, do we have an expression for Vmax? Well, of course we do. It's Vmax equals omega A, and we want A. So we have to find omega first. Vmax is 3 meters per second, so let's find omega. That is 2 pi over t, and like every time, I'm going to say it every time, I promise this. 2 pi over t is the same thing as 2 pi times frequency, since 1 over t is frequency. Anyway, I'm going to use 2 pi over t because it's very easy to find the period. So starting here from the origin, we're at 0, 0. We complete a cycle. We end up at 60. So that's the period is 60 seconds. I can plug that in for t and then find that the omega value is pi over 30. And therefore, it goes back into the Vmax. We solve for A, and it becomes 90 over pi, or in decimal form, about 28.6 meters. Pause again, solve part B. The maximum acceleration can be solved mathematically, but before we do that, I want to just talk about what it looks like on the graph. So if you look at a velocity time graph, as we are here, can you see the acceleration? Well, maybe not sort of directly, like it's not like the peak or anything, but you can see it because it's the slope. The slope at every instant of the tangent line to the curve would give you the acceleration at that moment. That's another way of saying the equivalent acceleration is the time derivative of velocity. So when is the slope maximized? In other words, when is the slope its steepest? Well, that occurs here at the beginning, here again at 30, here again at 60, and so on and so on. But you'll notice that there's an inverse relationship between the slope and the actual value of velocity. So what I mean by that is, for example, at the origin, look, what's the velocity here at time 0? Well, it's 0. I mean, we're not moving. If you have a velocity of 0, you're motionless at this instant. But the slope is maximized. In other words, the acceleration is maximized when the velocity is minimized. Is the opposite true? Well, here's where the velocity is maximized, right? What about the acceleration? Well, at this moment, the acceleration would be 0 because the slope of the tangent line would follow this dotted horizontal line. In other words, this dotted horizontal line has a slope of 0, as do all horizontal lines, and therefore the acceleration would be 0 when the velocity is maximized. Now let's try to calculate it. We have a formula for A max, which is omega squared A. We already know omega and A, so this is actually kind of easy. I'm just going to try to keep reminding you of common mistakes I've seen. So again, you're squaring a fraction, so you do square the numerator and the denominator. So this is pi squared over 30 squared, which becomes pi squared over 900. And then you multiply it by this other fraction, and you get pi over 10. And I didn't write it, but I'll just tell you the answer in decimal form is then just 0.31 meters per second squared.